Okay, welcome everybody to one of the last lectures of the semester. And in this little lecture, we would like to see the connections between Green's theorem and Stokes theorem and the divergence theorem and see how all these things are related to each other. Okay, so let's remember what Green's theorem is. So basically, I think of this as a theorem for things in the plane. So if I have a smooth, piecewise smooth curve bounding a region R, and we always want to orient things counterclockwise for our theorems. So that means if you're an ant walking along the curve, the region R stays to your left-hand side. And suppose that you have M and N, which are both functions of variables X and Y, that are continuous and their first partial derivatives are continuous. Then Green's theorem says that the line integral over C, over the curve C of m dx plus n dy is equal to the double integral over the region R of partial n sub x minus partial m sub y integrated with respect to the area. Okay. And then remember last week we derived a vector form of that same identity. I'm not going to go through the derivation again, but we saw that that's equivalent to thinking the integral over C of f dot dr is the double integral over R of f, the curl of f dotted with k dA. So to do that, you had to think of a vector field f as having the components m and n, and then 0. So in other words, you need, if you have a two-dimensional vector field to apply the curl to it, you're going to have to make it into a three-dimensional vector field because curls only make sense in 3 dimensions. So you just put a 0 in that third component. Okay. All right. And then this week we learned Stokes theorem, which says that if you have a piecewise smooth surface bounding with a boundary curve C, and you have a vector field on that open region, region S, then the integral over the line integral over that curve of the vector field f dot dr is the integral over the surface that the curve bounds of the curl of f dot d vector s. So remember what that notation means. On this side, that really means the curl of f dotted with the outward unit normal to the surface and then integrated with respect to surface measure. And then dot d vector r really is shorthand for f dotted with the unit tangent vector to the curve C integrated with respect to the arc length. Okay. And remember, how do you get the unit tangent vector from R? You take r prime of t and divide by the length of r prime of t, because r prime of t is a tangent vector, and then you have to make it into a unit vector. Okay, so we have those 3 theorems. And then finally, let's remember what the divergence theorem says. If you have a simple solid region with a boundary surface S and a vector field which is continuous on that region and has continuous first partials, then the integral over the surface of f dot n ds is the integral over the entire region of the divergence of f dv. Okay, so I think of Stokes theorem and the divergence theorem, at least the way we've stated it so far, as being 3-dimensional theorems. That's not really true. They are n-dimensional theorems, but we kind of stick to no more than 3 dimensions in this course. And the way Green's theorem is generally thought of as it's thought of as a 2-dimensional object. But I'm going to show you how to think that they're really all the same. But Green's theorem is both a version of Stokes theorem and a version of the divergence theorem if you look at them in the right way. All right, so let's look first at the connection between Green's theorem and Stokes theorem. So I'm going to take a vector field F, and remember in Stokes theorem, in Green's theorem, we have an m dx and an n dy. So I'm going to make a vector field out of that by going m n 0. Okay, and so the vector form of Green's theorem says exactly this. Okay, so that's our vector form of Green's theorem. And the derivation of that and how you get that from Green's theorem is in the lectures last week. Okay, so now think of R as a flat surface, that is, that it lies in the XY plane. Then what's the outward unit normal to something that lies in the xy plane? Well, it's something that the unit vector that points in the direction of z, in other words, k. So in that case, n is k. So now let's rewrite this integral. So the line integral of f dot dr is going to be the integral of the curl of f dotted with, what doesn't matter whether I write it as n or k in this way, but when you take a vector and you dot it with n and then it's integrated with respect to surface measure, that's what you shorthand what you mean by the curl of f dot ds, which is exactly Stokes theorem. Okay, so the vector form of Green's theorem is exactly Stokes theorem in 2 dimensions. Okay? So it's really the same thing. All right, so that was short and sweet. But remember, we did some work to show that that's the same thing as Green's theorem last week. All right, so now let's get the connection between the divergence theorem and Green's theorem. So again, here's our divergence theorem written down. And how do we do this? Okay, so S is the boundary of the region E, and N is the outward unit normal to the surface S. Okay, and now we want a 2-dimensional analog. So we start by looking at Green's theorem for a minute. And then I said, and C is the boundary curve for the region R. All right, so here's my setup. Think of the vector field F as the vector field N minus M. Okay, and now I'm going to parameterize the curve C, which bounds that region R. Let's call it parameterization x of t, y of t. Then what's the tangent vector to that curve? It's r prime, which is x prime, y prime. I didn't write it down, but what would the unit tangent vector be? It would be r prime divided by the length of r prime. So what's a normal vector to the curve? Well, it's any vector that when I dot it times the tangent vector, I get 0. So one of those vectors would be y prime minus x prime, because when I take the dot product of this with that vector, I get 0. And if I want to make that into a unit vector, I simply divide by its length. So that's what I've done there. So there's a normal vector to my curve. Okay. Okay. Now, on the other hand, what's the divergence of this vector field that I constructed before f? So here's the gradient vector, and I dot it with my vector f. So that gives me n sub x minus m sub y. Wow, that's looking a little familiar, isn't it? So if I integrate the divergence of f over the region R with respect to the area, then that's the same thing for this vector field as the integral over R of n sub x minus m sub y dA, which by Green's theorem is the same thing as the line integral over C of m dx plus n dy. All right, so now we'll keep that in mind. So the divergence of f integrated over R gives me the line integral of m dx plus n dy. All right. Now let's look for a minute at what is f dot n. So here's f, here's my normal vector n. Take the dot product. That gives me an ny prime over the length of r prime plus mx prime, because the 2 negatives cancel, divided by the length of r prime. Okay. And remember that ds for us, but not for us, as we derived much earlier in the semester, is length of r prime of t dt. So if I look at the line integral of f dot n ds, that is, all right, I write in my f dot n, I write in my ds. I notice that the length of r prime, this should not be a squared, that's a typo. It's going to be the wrong color, but that's a typo. There's no square there. It's just divided by the length of r prime. So the length of r prime cancels out. I'm going to write it as 2 integrals for a second. This is n y prime of t dt plus the line integral of m x prime of t dt, because the r primes are gone. Remember that y prime of t dt is shorthand for dy, or dy is shorthand for that. Dx is shorthand for x prime of t dt. Okay. And so this is the line integral over c of m dx plus n dy. But by what we found on the previous page, that's the divergence of F integrated over R. Okay. So what we just showed is that using Green's theorem, we have the integral over the line integral of F dot n ds is equal to the double integral over the region R of the divergence of F dA, which is the exact two-dimensional analog of the divergence theorem. Okay. All right, so Green's theorem really is Stokes theorem and the divergence theorem, the two forms of it. One is one is the other. When you look at it in the right way, and it's just a Green's theorem is just a two-dimensional version of those theorems, Green, divergence, and Stokes. And actually, if you state them carefully, Stokes theorem and the divergence theorem both have analogs in n dimensions. Although it's a little harder to state Stokes carefully in n dimensions because you got to figure out how to replace the curl. Okay. Okay, that's it for today. So short and sweet, and I will see you again soon.